So here we're going to talk about 4 types of bonding. The first we talked a ton about. First, ionic. So here, ionic made of formula units, whereas covalent or molecular made of molecules. Only difference, molecule is a separate piece. Think one H2O molecule. That's one piece. Whereas if I had one NaCl, that's really hard to get because we saw in one of my PowerPoints that NaCl is usually a part of a bigger crystal structure. Because of Na and Cl having these positive and negative charges, it's going to be attracted to more than just the Na or the Cl. It's going to be attracted to a different Cl, and we get these larger crystal structures. Also, you can think of ionic being made of ions, hence the name, whereas covalent or molecular compounds, these are made of atoms. So here, ionic held together by that positive-negative attraction, which we call an ionic bond, formed when electrons are transferred from our metal to our nonmetal. Whereas covalent, held together by covalent bonding or the shared electrons, so sharing between two nonmetals. So here our metal loses electrons, our nonmetal gains. Well, if I have two things that want to gain electrons, that can't happen. So instead they opt to share. And again, the whole idea is getting to 8. So same thing, satisfy octet rule because octet's stable and stable is happy. More about ionic and covalent. So ionic, strong bond. If you go in, so to talk about melting and boiling points, go and melt salt. I think I had some, I can't remember what hour we looked it up one day. It was like 1100 degrees or either way. It was somewhere around 1000, really high melting point to go melt table salt. Whereas covalent bonds, weaker. A single covalent bond is very weak. A double covalent would be a little stronger. Triple covalent would be our strongest covalent, but even then, still relatively weak, which causes these things to have low melting and boiling points. So you think sugar. Sugar is a covalent bond. If I want to melt sugar to make candy, well, that I really only need about 180 degrees Fahrenheit, so something around maybe 90, 95 degrees Celsius. If that, not quite sure there on my conversion. Either way, it's a lot lower, a lot easier to do to get these to melt and boil versus something like salt. So because of these strong bonds, these things usually solids, and those solids are usually pretty hard. So think about trying to scratch a piece of salt. It would be tough. You might be able to get it to flake off, whereas covalent bonds, often liquids or gases, or kind of a mushy solid. So think like butter. Butter's an amorphous solid made up of covalent bonds between carbons and hydrogens. So yeah, you can have solids, but they're generally pretty soft. Think water, alcohols. These are all liquids. Gases, you have even your diatomics or covalent bonds. Oxygen gas, carbon dioxide gas. These are all covalent. When you dissolve ionic compounds in water, you end up with electrolytes, if it's soluble. So we saw in our precipitates lab that not all of these are soluble. If they are, they form electrolytes. We'll talk more about that later on. But meaning electrolytes, they allow electricity transfer in water. So this is why you can't go swimming in your swimming pool in a lightning storm, because if you do and lightning does strike, well, that electricity is just going to flow right through that water, right into you. You are made up of a bunch of water with an electrolytes in it, so it pass right through you and kill you. Whereas here, these things usually insoluble in water, says usually, not all the time. We can get alcohols and things to dissolve in water because of specific properties of that compound, but usually insoluble in water. Think oil and water, they separate. Metallic bonding, don't worry, much shorter than ionic covalent. Metallic bonding here, all valence electrons, they delocalize. So whatever, pick your metal, doesn't matter what. You're gonna let go of all their valence electrons to kind of form this cloud. So here's my cutout. We have metal, a whole bunch of metals, they let go of their electrons and they delocalize. So what you end up with is some cations with just kind of electrons everywhere. These electrons are free to move around, like maybe, I don't know, in a circuit of some kind, like in your wire or something like that within your house to power your electronics, whatever. These electrons can flow back and forth as you flip the switch and turn it off, things like that. So it's often referred to as a sea of electrons, where if you think of the sea, you know, the tide going in and going out, well, that's what happens. So this electron not tied to either of these, so it can flow back and forth and it's just going to be replaced by another one. So that's why metals are good conductors of electricity. There is a strong attraction though between the positive and the negative, and it would be awfully hard to just pull one electron away because of that positive-negative attraction between your cation, your positive, and then the electron in the cloud. Our fourth and final type of bonding, and then hooray, Mr. Sacre is going to shut up. Hydrogen bonding, this is the attraction between dipoles. Grab a marker here. Remember, dipoles caused by, you know, our electronegativity chart. We look and see, hey, is there a big enough difference between, you know, this atom to cause that polar covalent bond? This type of bonding is relatively weak, and it's an intramolecular force, so between different molecules, whereas everything we've talked about before is inter, or in between kind of that one compound. These relatively weak, and it's only about 1/10 of kind of a single covalent bond. So this is our weakest that we'll talk about. Sounds like a good multiple choice question to me. I'm going to erase this and talk about what this means here in a second. When we talk about hydrogen bonding, it doesn't have to be water, but we use water as a big example. Really, for hydrogen bonding, all you need is hydrogen, hence the name, as well as something that's really electronegative, like fluorine or nitrogen, or in this case, oxygen. But how this all works is, well, fluorine wants the electrons more, so it's going to pull them, and we get this dipole. And let's say I have another, and we'll call this a fluorine again. Let's say I have another one. Well, if this side was our partial positive and this side our partial negative, well, this positive is going to be attracted to this partial negative, and so on, and that's what happens. So in water, that's what's happening here. We have partial positives at this end and partial negatives at the oxygen. Well, they're attracted to each other, so I have a negative and a positive, a negative and a positive, and so on. Well, what this causes in water, as well as others, but this holds our molecules closer together. And in water, it's about 15% closer than normal liquids, or liquids that don't have this hydrogen bonding. This gives water some kind of unexpected properties. One, higher than expected boiling point. So this is why when you go and make your spaghetti or your macaroni and cheese, that it takes so long for that water to boil. This water molecule likes this water molecule, which likes this water molecule. There's an attraction. And boiling is, well, getting, you know, this piece to leave the system and leave the pot into the air. That's what boiling is. How much energy does it take to do that? Well, because of this extra attraction, it takes extra energy. And that's why water's boiling point is much higher than kind of similar liquids. This also causes surface tension. So hit pause, go get a glass of water, fill it up as much water as you can, right to the top, and then just keep adding one drop at a time. Eventually what you'll get is this dome over the top of your glass. And if you take the lead out of your pencil or a paper clip, I bet you could get that paper clip to sit right on top of that water. That's surface tension, and it's caused by this water liking this water, so through hydrogen bonding. This is why water forms droplets. It's because of surface tension. This is, if you've ever seen those water spiders that kind of skate along the surface of the water, it's because of this. Also, notice this one I drew with kind of this, if you look at this water molecule, it has kind of 4 hydrogen bonds, or 4 attractions. It's not a true bond, but 4 attractions. So it has a possibility of 4. On average, liquid water has about 2.6 to 3.4 of these bonds, and that probably depends on temperature. But what happens is, when we start to cool things down, when water starts to freeze, these things all start lining up in a nice crystal pattern. And what happens is, because of the arrangement, this actually causes the volume of these crystals to be bigger. I know we said it holds them closer, but it usually doesn't have 4, and now we get a very rigid pattern. So this causes them to kind of fit this very specific pattern, very specific crystal. And if we think about density of water, so normal water density, mass divided by volume, but we start freezing it and start creating ice, well, what happens? Well, instead of, density is equal to mass divided by, we said volume increases, so a bigger volume. Well, if I start dividing by a bigger number, density is going to get smaller. And we know that things with lower densities than liquid water, they float. This is why water floats. And if water didn't float, because of kind of this property, if water didn't float, how would plants and animals survive in the winter at the bottom of a pond? So what if a pond, the ice started at the bottom and it just kept being cold and never thawed? Well, that ice is just going to keep building up, building up, building up, and start pushing the fish and the plants and stuff just out and out until eventually there's no water. So because ice, lower density, causing it to float, we don't have to worry about that. So just something as simple as this little extra attraction, pretty important into pretty much every ecosystem that's in cold climates. So that's bonding, 4 types. Review those. Obviously know the most about ionic and molecular. That's the one we spent the most time on talking here. But also know how metallic bonding, that sea of electrons, and then here kind of those weird properties that hydrogen bonding gives to water.